Feature importance tells you what mattered, not how it changed predictions. PDP and ICE plots in scikit-learn show the missing shape. This is the pattern you'll be able to implement by the end, which computes the partial dependence curve and aligns it with ICE traces. I'm Professor Pi, teaching AI foundations with simple Python. Interpreting a black box model is a common pain. You might know which features rank high, but not how changing a feature value moves a prediction. Partial dependence plots give the average response as one feature varies. Individual conditional expectation traces show single sample responses. Together they reveal whether the average hides big personal differences or nonlinear effects you should care about. At a high level, we want the global average trend and the individual trajectories for the same feature grid. That tells you if an average trend is trustworthy for most people, or if a few cases swing wildly. It also helps decide where to audit or simplify a model for fairness and debugging. We will build a compact demo. It trains a tree ensemble on a common regression dataset, computes a smooth partial dependence for body mass index, extracts per sample ICE curves, finds a high sensitivity patient, and then compares the personal effect with the average. This makes the difference between group signals and personal reactions obvious before you run plots. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Now, let us train a baseline model so the interpretation steps have something real to explain. This snippet fits a gradient boosting regressor on scikit-learn's diabetes data and gives you a reproducible train test split to work with. It loads X and Y plus feature names so later steps can refer to columns by name. Uses train test split random state equals 42 to create xtrain and xtest. Trains GBR on the training fold and prints gbr.score so you can see how much variance the model captures before any diagnostics. The printed train R2 is your baseline fixed strength that frames the interpretation that follows. We have a trained model and a held out fold. Next, we compute the partial dependence for BMI to see the average model response and establish a shared grid. This example extracts the average BMI partial dependence curve with scikit-learn's partial dependence and returns both the evaluation grid and the averaged response. FeatureNames.index finds the BMI column, so the helper evaluates the right axis using the test fold. The outputs go into BMI grid and BMI average, so AVG trend can compare the first and last points. Raising grid resolution smooths the curve at the cost of more work, while lowering it runs faster but coarser. The printed average BMI trend reports the net average change across the BMI range. A population average is useful, but it can hide extremes. So next we pull every individual ICE trace on the same grid and search for the patient whose prediction shifts most. This code retrieves individual BMI ICE curves so you can spot the most sensitive sample. Kind individual switches partial dependence into ICE mode, and method brute forces tree ensembles to compute true per sample responses on the shared BMI grid. ICE curves holds the aligned trajectories. Slopes computes each curve's change from start to finish. And NP arcsort surfaces the largest movers. Focus ID picks the steepest curve for later checks, while max slope keeps its signed change. The printed max ICE slope highlights how extreme that individual's BMI effect is compared to the group. Once you can find a strong individual effect, a useful next check is whether BMI swings more than another clinical feature. We compare ranges to prioritize investigation. This snippet compares BMI and blood pressure average partial dependence ranges to see which feature moves predictions more. Feature names.index locates the BP column, and partial dependence reuses the established grid length, so both curves remain aligned. np.ptp reduces each average curve to a single range metric, and range ratio divides BMI swing by blood pressure swing. A larger ratio means BMI drives a stronger average response than blood pressure here, and the printed PDP range ratio gives you that prioritization number. Now, we contrast the steep icy patient against the global PDP by forcing that patient's BMI to the grid endpoints and seeing the model predictions change. This example contrasts the steep ice case against the global PDP by toggling BMI on the same patient between the grid endpoints. Sample pulls the focus ID row found earlier, and low sample and high sample overwrite BMI with the endpoints from BMI grid. gbr.predict evaluates both altered records to produce pred low and pred high. So ICE delta measures that subject's actual response. Comparing ICE delta to AVG trend shows whether the personal trajectory departs from the population average. And the printed sample delta and PDP delta reveal how much that chosen patient's shift diverges from the global expectation. This compact flow maps directly to real projects. Swap the diabetes set for your cohort, run the same grid across patients, and log per sample deltas for auditing. Those comparisons help choose features for simpler surrogates or for targeted human review when individual deviations look risky. PDP gives you the model's average response for a feature, and ICE lays out each sample's trajectory so you can spot heterogeneity. The key caveat is simple. Averages can hide extreme individuals, so don't treat a PDP as universally true. Next step, tune the partial dependence grid resolution and measure runtime so you can balance smoother curves against extra computation as you scale. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.